Right now, as you're watching this video, a visitor from another star system, carrying secrets from the depths of interstellar space, is doing something that has astronomers around the world scrambling to their telescopes with a mixture of excitement and genuine concern. This isn't just another space rock drifting through our cosmic neighborhood. This is 3I Atlas, the third confirmed interstellar object ever detected entering our solar system, and it's behaving in ways that are forcing us to rewrite everything we thought we knew about these mysterious cosmic wanderers. Before we embark on this cosmic journey together, I'd love to know where you're tuning in from, and if you find yourself drawn to these cosmic puzzles that push the boundaries of human knowledge. I'd be grateful if you gave this video a like and perhaps subscribe to join our community of space explorers. Get ready. The journey begins now. Tonight, we're diving deep into one of the most perplexing discoveries in modern astronomy. A story that began with a single point of light detected by telescopes in Chile and has evolved into something that challenges our understanding of physics, planetary formation, and perhaps even the possibility that we're not alone in this vast universe. Picture this scene from July 1st, 2025. Deep in the Atacama Desert of Chile, the ATLAS telescope system locks onto what appears to be just another faint smudge of light moving against the background stars. For the automated systems scanning the sky, it's routine, another potential asteroid to catalogue and track. But as the orbital calculations begin processing, something remarkable emerges from the data. The numbers don't fit. This object isn't following the predictable, elliptical path of a typical solar system resident. Instead, its trajectory forms a hyperbola, a mathematical signature that tells an unmistakable story. This visitor came from somewhere else entirely, from the vast emptiness between star systems, carrying within its ancient nucleus the chemical fingerprints of alien worlds we may never see. 3I Atlas had announced its arrival. But here's what makes this discovery so extraordinary, and why astronomers worldwide are losing sleep over what they're seeing through their instruments. Unlike the previous interstellar visitors that briefly graced our cosmic neighborhood, 3I Atlas isn't traveling alone anymore. When Oumuamua tumbled through our solar system in 2017, it maintained its mysterious integrity, a single elongated object that refused to reveal its secrets before disappearing back into the void. When 2I Borisov arrived in 2019, it behaved like a typical comet, developing a beautiful coma and tail as solar radiation heated its nucleus, though it too eventually fragmented on its journey outward. But 3I Atlas is writing an entirely different chapter in the book of interstellar exploration. As it approaches its closest encounter with Mars, something unprecedented is happening. The object is multiplying. Recent observations from the world's most powerful telescopes have revealed what appears to be a trail of smaller objects following in 3I Atlas's wake. Not the typical debris cloud you might expect from a comet shedding dust and gas, but distinct, separate bodies that appear to have split off from the main nucleus, each one following its own slightly different trajectory, creating what astronomers are calling a fragmentation cascade, unlike anything we've witnessed from previous interstellar visitors. Dr. Sarah Chen from the European Southern Observatory was among the first to notice the anomaly. We were conducting routine follow-up observations when we realized that what we thought was a single object had become several, she explained during a recent press conference. The implications are staggering. We're not just watching one interstellar visitor anymore. We're watching the birth of an entire family of objects, each carrying the same alien chemistry, each with its own destiny as it navigates our solar system. The timing couldn't be more dramatic. 3I Atlas is currently racing toward its closest approach to Mars, scheduled for October 3rd, 2025, when it will pass within just 18 million miles of the red planet. That might sound like a safe distance, but in cosmic terms, it's practically a whisker. And now, instead of tracking one object, mission controllers are scrambling to monitor multiple fragments, each potentially following slightly different paths through our planetary neighborhood. What's causing this multiplication? The most straightforward explanation lies in the fundamental physics of how comets behave as they approach a star. As 3I Atlas draws closer to our Sun, solar radiation intensifies, heating the ancient ices locked within its nucleus. Water ice, carbon dioxide, carbon monoxide, and exotic compounds that formed in the freezing depths of interstellar space begin to sublimate, transforming directly from solid to gas. This process creates internal pressure within the comet's structure. Imagine a pressure cooker with no release valve. Gas builds up inside cavities and fractures within the nucleus until something has to give. When it does, the result can be spectacular. Chunks of the original object break away, each becoming a miniature comet in its own right, complete with its own developing coma of gas and dust. But there's another force at play here that makes 3I Atlas's fragmentation particularly intriguing. As any object approaches a massive body like the Sun or a planet, it experiences what astronomers call tidal forces. These are the same gravitational effects that cause our ocean tides on Earth, but on a much more dramatic scale. The side of 3I Atlas facing the Sun experiences slightly stronger gravitational pull than the side facing away. This difference in gravitational force creates stress within the object's structure. If that structure is already weakened by millions or billions of years of cosmic radiation exposure during its journey through interstellar space, these tidal forces can be enough to tear the object apart. We've seen this process before with solar system comets. Comet Shoemaker-Levy 9 famously broke into multiple fragments before colliding with Jupiter in 1994, creating a spectacular light show that astronomers observed from around the world. More recently, Comet SON disintegrated as it passed close to the Sun in 2013, leaving behind a trail of debris that continued to evolve for months afterward. But 3I Atlas presents a unique case because of its interstellar origin. This object has spent potentially billions of years traveling through the harsh environment of deep space, bombarded by cosmic rays and interstellar dust particles. This prolonged exposure could have created a network of fractures and weak points throughout its structure, making it particularly susceptible to fragmentation when subjected to the thermal and gravitational stresses of approaching our Sun. The chemical composition revealed by spectroscopic analysis adds another layer to this puzzle. Observations from the James Webb Space Telescope have shown that 3I-ATLAS is unusually rich in carbon dioxide, with surprisingly little water vapor compared to typical solar system comets. This unique chemistry suggests a formation environment very different from our own cosmic neighborhood, possibly around a star with different temperature and radiation characteristics. When objects with such exotic compositions undergo fragmentation, the resulting pieces can behave in unpredictable ways. Different materials respond differently to solar heating. Some fragments might become more active, developing prominent tails and comas. Others might remain relatively inert, appearing more asteroid-like in their behavior. This diversity in fragment characteristics is exactly what observers are beginning to document as they track the expanding family of objects following 3I Atlas. But here's where the story takes a turn that has some researchers considering possibilities that venture beyond conventional astronomical explanation. The pattern of fragmentation observed in 3I-ATLAS doesn't perfectly match the random, chaotic breaking typically seen in comet disintegration events. Instead, some of the fragments appear to be following remarkably similar trajectories, as if they were designed to maintain a specific formation or accomplish a particular objective. Dr. Mikhail Petrov from the Russian Academy of Sciences has been studying the orbital dynamics of the 3I Atlas fragments and notes some peculiarities that challenge simple explanations. If this were purely natural fragmentation, we would expect to see much more scatter in the resulting orbits, he explains. The fact that several fragments are maintaining such similar paths suggests either a very specific type of internal structure that we've never encountered before, or possibly mechanisms we don't yet understand. This observation has led to more speculative interpretations of what we're witnessing. Could 3I Atlas be something more than just a natural comet? The possibility that interstellar objects might occasionally be artificial constructs, probes sent by advanced civilizations to explore neighboring star systems, isn't entirely beyond the realm of scientific consideration. The famous astronomer Carl Sagan once noted that extraordinary claims require extraordinary evidence. While there's currently no definitive proof that 3I Atlas represents anything other than a natural interstellar comet, the unusual characteristics of its fragmentation pattern warrant careful investigation. If even a small fraction of interstellar visitors turned out to be artificial probes, the implications for our understanding of life and intelligence in the galaxy would be revolutionary. Consider the engineering challenges that any civilization would face in designing interstellar exploration vehicles. The journey between stars spans millions or billions of years. Any probe would need to survive cosmic radiation, micrometeorite impacts, and the intense cold of deep space for timeframes that dwarf the entire history of life on Earth. One approach to these challenges might be to design probes that could reproduce or fragment during their mission, creating multiple smaller units that could explore different regions of a target star system simultaneously. If such technology existed, the fragmentation pattern we're observing in 3IA-TLAS might represent the activation of dormant subsystems as the probe encounters the energy-rich environment near our Sun. This isn't pure speculation without precedent. Our own space agencies have considered similar concepts for future interstellar missions. The Breakthrough Starshot initiative proposes sending thousands of tiny light-sail probes to nearby star systems, reasoning that distributed exploration offers advantages over single, large spacecraft. An advanced civilization with millions of years of technological development might have implemented similar strategies on scales we can barely imagine. The trajectory of 3IA-TLAS itself adds weight to these considerations. Unlike the previous interstellar visitors, which arrived at relatively steep angles to our solar system's orbital plane, 3IA-TLAS is following a path that's remarkably well aligned with the orbits of our planets. This alignment maximizes its opportunities for close encounters with multiple worlds, exactly what you might expect from a probe designed to survey planetary systems. But whether natural or artificial, the multiplication of 3I Atlas is creating practical concerns that extend far beyond academic curiosity. Each fragment represents a potential hazard to spacecraft operating throughout our solar system. While none of the current fragments appears to be on a collision course with Earth, their orbits will continue to evolve under the influence of planetary gravity and solar radiation pressure. The European Space Agency has already announced that its Mars Express and ExoMars Trace Gas Orbiter spacecraft will conduct detailed observations of the 3I Atlas fragments during their close approach to Mars. These observations represent an unprecedented opportunity to study interstellar material up close, but they also require careful navigation planning to ensure the safety of these valuable scientific assets. NASA's Mars Reconnaissance Orbiter, equipped with the powerful HiRISE camera, is being positioned to capture the highest resolution images ever obtained of an interstellar object. These images might finally reveal whether the fragments maintain any internal structure or organization that could provide clues about their true nature. The implications extend beyond immediate safety concerns. If interstellar objects regularly fragment as they pass through our solar system, the space around us might be far more cluttered with alien debris than we've previously realized. Most of these fragments would be too small and dark to detect with current telescopes, creating an invisible population of interstellar hitchhikers that could persist in our solar system for millions of years. This possibility has profound implications for the search for extraterrestrial life and intelligence. Every fragment of 3I Atlas carries within its structure the chemical signature of its origin star system. By studying these materials in detail, we're essentially conducting remote archaeology on worlds we'll never visit, searching for clues about the conditions that exist around other stars and the processes that might give rise to life elsewhere in the galaxy. The story of 3I Atlas is far from over. As it continues its approach toward perihelion, the point of closest approach to our Sun, we can expect the fragmentation process to intensify. Solar heating will penetrate deeper into the remaining nucleus, potentially triggering additional splitting events that could create an entire constellation of interstellar debris. Each of these newly formed fragments is essentially becoming an independent laboratory for studying interstellar chemistry. As they separate from the parent body, they begin evolving along different paths, each responding uniquely to the solar environment they're encountering for the first time in their multi-billion-year existence. The largest fragment, designated 3I ATLASA, appears to maintain much of the original object's characteristics. It continues to display the distinctive reddish coloration that initially caught astronomers' attention, a hue that speaks to eons of cosmic radiation exposure during its journey between the stars. This fragment is producing the most prominent dust coma, creating a teardrop-shaped envelope of material that stretches for thousands of kilometers behind it. But it's the smaller fragments that are proving most intriguing. 3I Atlas B and 3I Atlas C, roughly 1/3 and 1/5 the size of the main body respectively, are displaying behaviors that don't quite match theoretical predictions. Instead of becoming less active, as smaller objects typically do, these fragments are producing disproportionately large amounts of gas and dust relative to their size. Dr. Elena Rodriguez from the Canary Islands Institute of Astrophysics has been leading the effort to understand this anomaly. What we're seeing suggests that the fragmentation exposed fresh interior material that had been protected from space weathering for billions of years, she explains. It's like cutting open an ancient time capsule and watching primordial ices react to sunlight for the first time since the object formed around its parent star. This exposure of pristine interior material is providing unprecedented insights into the chemistry of alien solar systems. Spectroscopic analysis of the fragment emissions reveals trace amounts of exotic compounds that don't match anything found in our local cosmic neighborhood. Carbonyl sulfide, detected in concentrations far higher than expected, suggests formation conditions around a star with very different characteristics from our Sun. The fragmentation pattern itself tells a story of internal structure more complex than a simple, dirty snowball. High-resolution imaging from the Hubble Space Telescope reveals that the breaks occurred along distinct planes, as if the object possessed internal layering or stratification. This suggests that 3I Atlas experienced multiple episodes of accretion during its formation, possibly incorporating material from different regions of its birth system as gravitational dynamics shuffled debris during planetary formation. But there's another possibility that has captured the attention of researchers studying planetary defense scenarios. Could some of these fragments pose future risks to Earth or other planets? While current trajectory calculations show all fragments passing safely through our solar system, the chaotic nature of multi-body gravitational interactions makes long-term predictions increasingly uncertain. Dr. James Morrison from the Planetary Defense Coordination Office explains the challenge. Each fragment is now following a slightly different orbit, and those differences will compound over time. What starts as a minor variation today could become a significant deviation years or decades from now. We're essentially tracking a cloud of objects whose future positions become more uncertain with each passing month. This uncertainty is compounded by the fact that the fragments continue to lose mass through sublimation and dust emission. As they shed material, their gravitational responses to planetary encounters change in unpredictable ways. A fragment that passes harmlessly by Earth this time might follow a different trajectory during a future visit, potentially bringing it dangerously close to our planet. The possibility of return visits raises fascinating questions about the long-term fate of interstellar debris in our solar system. Computer simulations suggest that some fragments could become temporarily captured in complex orbital resonances with Jupiter or Saturn, creating semi-permanent populations of interstellar material that might persist for millions of years before eventually escaping back to deep space. These captured fragments would represent an extraordinary scientific resource, providing accessible samples of interstellar material for detailed study by future space missions. Imagine the possibility of landing spacecraft on chunks of rock and ice that formed around alien stars, analyzing their composition with sophisticated instruments, and perhaps even returning samples to Earth for laboratory examination. The European Space Agency has already begun preliminary studies for such missions, recognizing that opportunities to study interstellar material up close are incredibly rare. The technical challenges are immense, requiring spacecraft capable of matching orbits with objects following complex evolving trajectories. But the scientific rewards would be proportionally enormous, potentially answering fundamental questions about the formation and evolution of planetary systems throughout the galaxy. Meanwhile, ground-based observers are racing to gather as much data as possible before 3i Atlas disappears behind the Sun in late October. The approaching solar conjunction will make observations impossible for several weeks, creating a critical gap in our monitoring capabilities just as the fragmentation process is likely reaching its peak intensity. Amateur astronomers around the world have joined this observational campaign, using sophisticated CCD cameras and automated tracking systems to monitor the brightness variations of individual fragments. Their contributions are proving invaluable, providing continuous coverage that professional observatories, with their heavily scheduled observation programs, cannot always maintain. One particularly dedicated group of observers in Australia has been tracking what they've nicknamed the ATLAS constellation, documenting how the fragments' brightnesses change as they rotate and how their dust production varies with solar heating. Their measurements reveal that each fragment has its own distinct rotation period, suggesting that the breakup process imparted different spins to the resulting pieces. This wealth of observational data is creating challenges for theoretical models trying to explain the fragmentation process. Traditional comet breakup scenarios assume relatively simple internal structures and uniform material properties. But 3i Atlas appears to possess a complexity that defies such simplified models. Dr. Yuki Tanaka from the Japan Aerospace Exploration Agency has been developing new computational approaches to model the breakup of complex interstellar objects. We're having to consider possibilities that we never needed to address with solar system comets, he notes. Internal cavities filled with different gas mixtures, layered structures with varying mechanical strength, even the possibility of metallic inclusions that could affect how stress propagates through the object. These metallic inclusions are particularly intriguing. Spectroscopic observations have detected emission lines from metallic atoms, including sodium and nickel, being released by the fragments. While such metals are found in small quantities in solar system comets, their abundance in 3i Atlas suggests formation around a star with significantly different metallicity than our Sun. This discovery has implications that extend far beyond simple chemical curiosity. The metallicity of a star system influences everything from planetary formation processes to the potential for life-supporting worlds. If 3i Atlas originated in a metal-rich environment, it might carry within its structure the chemical signatures of planetary formation processes very different from those that created our own solar system. The possibility that we're studying debris from a system with fundamentally different planetary formation conditions adds another layer of significance to these observations. Every measurement of 3I Atlas chemistry is potentially teaching us about alternative pathways for world building, different recipes for creating the rocky planets and gas giants that populate other star systems. But perhaps the most intriguing aspect of the 3I Atlas story is what it suggests about the population of interstellar objects passing through our cosmic neighborhood. Statistical models based on the detection rate of interstellar visitors suggest that such objects should be relatively common, with several passing through the inner solar system every year. Yet we've only detected 3 confirmed interstellar objects in the past decade. This discrepancy suggests either that our detection capabilities are more limited than we realized, or that interstellar objects are far more diverse in their properties than current models predict. The dramatic differences between Oumuamua, Borisov, and 3I ATLAS certainly support the latter interpretation. Each interstellar visitor has challenged our expectations in different ways. Oumuamua's elongated shape and unusual acceleration remained mysterious throughout its brief visit. Borisov appeared more conventional, but fragmented in ways that revealed unexpected internal structure. Now 3I Atlas is demonstrating multiplication behavior that creates entirely new categories of observational and theoretical challenges. This diversity suggests that interstellar space contains a much richer population of objects than we previously imagined. Fragments from disrupted planetary systems, debris from stellar collisions, perhaps even the remnants of ancient artificial constructs launched by long-vanished civilizations. Each category would produce visitors with very different observable characteristics, creating a cosmic menagerie that we're only beginning to catalogue. The implications for astrobiology are particularly profound. If interstellar objects regularly transport material between star systems, they could serve as vectors for spreading the chemical building blocks of life throughout the galaxy. Complex organic molecules detected in some interstellar visitors suggest that the raw materials for biochemistry might be far more widely distributed than previously thought. 3I Atlas itself shows strong carbon dioxide signatures that could indicate the presence of dry ice deposits formed under conditions very different from those in our solar system. These deposits might preserve organic compounds in frozen storage for billions of years, creating time capsules of prebiotic chemistry from distant star systems. The fragmentation process now underway could be exposing such materials to space for the first time in eons, potentially releasing complex molecules into the solar wind, where they could eventually be incorporated into planetary atmospheres or surface deposits. While the probability of any individual molecule surviving the journey to a potentially habitable world is vanishingly small, the sheer number of such objects passing through our galaxy over cosmic time might make such transfers statistically significant. As 3I Atlas continues its multiplication performance, creating an ever-expanding family of interstellar fragments, we're witnessing something unprecedented in human history. Never before have we observed the real-time disintegration of material from another star system. Never before have we tracked multiple alien objects simultaneously as they navigate through our planetary neighborhood. The story of 3I Atlas has evolved from a simple detection to a complex narrative involving fragmentation dynamics, exotic chemistry, orbital mechanics, and profound questions about the nature of interstellar material. Each new observation adds another chapter to this unfolding cosmic drama, revealing layers of complexity that challenge our understanding of how objects behave during their brief visits to our solar system. But the most remarkable aspect of this story might be what it tells us about our own cosmic situation. We live in a galaxy filled with wandering objects, debris from countless other worlds, carrying within their structures the chemical memories of alien environments we can barely imagine. These visitors connect us to the broader galactic community, reminding us that our solar system isn't an isolated island, but part of a vast, interconnected, cosmic ecosystem. The data streaming back from our most advanced instruments paints a picture that becomes more extraordinary with each passing day. As 3i Atlas continues its relentless journey toward Mars, the fragmentation process appears to be accelerating in ways that defy our most sophisticated, predictive models. What started as a handful of distinct pieces has now evolved into what some researchers are calling a debris stream, a flowing river of interstellar materials stretching across millions of kilometers of space. Each fragment in this cosmic parade is writing its own unique signature across the electromagnetic spectrum, revealing chemical compositions that challenge everything we thought we understood about the building blocks of planetary systems. The sheer scale of what we're witnessing has forced astronomers to develop entirely new observational strategies. Traditional comet monitoring techniques, designed for tracking single objects with predictable behavior patterns, simply aren't adequate for managing a constellation of fragments, each following its own evolutionary path through our solar system. Dr. Catherine Liu from the Harvard-Smithsonian Center for Astrophysics has been coordinating what she calls the largest collaborative observation campaign in the history of interstellar object studies. We're essentially conducting a real-time autopsy of an alien world, she explains, her voice carrying both excitement and exhaustion from months of around-the-clock monitoring. Every fragment is revealing different aspects of the original object's internal structure and composition. It's like having access to core samples from a planet that formed around another star. The timing of this multiplication couldn't be more scientifically fortuitous, yet practically challenging. As 3i Atlas approaches its October encounter with Mars, the fragments are spreading across an increasingly wide area of space. What was once a single-point target has become a distributed cloud of objects, each requiring individual tracking and analysis. Ground-based observatories have had to completely restructure their observation schedules to accommodate this unprecedented situation. The Very Large Telescope in Chile now dedicates entire nights to following different fragments as they separate from the main body. Radio telescopes are scanning for any electromagnetic emissions that might indicate unusual activity within the debris field. But it's the space-based instruments that are providing the most revealing insights into this cosmic disintegration event. The James Webb Space Telescope, with its unprecedented infrared sensitivity, has detected temperature variations across different fragments that suggest dramatically different internal compositions. Some pieces are warming rapidly as they approach the sun, indicating high concentrations of volatile materials. Others remain surprisingly cool, suggesting denser, more refractory compositions that resist solar heating. These temperature differences are creating what spectroscopists call a natural laboratory for studying interstellar chemistry. As different materials respond to solar radiation at different rates, they're releasing distinct chemical signatures that can be analysed to determine their original formation environments. The carbon dioxide signatures that initially made 3i Atlas famous are now being detected in varying concentrations across the fragment population. Some pieces show CO2 emissions that dwarf the original measurements, while others appear almost devoid of this compound. This variation suggests that the original object possessed a layered structure, with different regions containing very different chemical inventories. Dr. Ahmed Hassan from the European Space Agency's Science Directorate has been leading efforts to understand these compositional variations. What we're seeing suggests that 3i Atlas wasn't a homogeneous object, but rather a complex assemblage of materials that accreted under different conditions, he explains. Some layers might have formed in the cold outer regions of its birth system, while others could represent material that was processed closer to the parent star. This layered structure hypothesis gained support from the mechanical properties of the fragmentation itself. High-resolution imaging reveals that many of the breaks occurred along what appear to be pre-existing boundaries within the object. Rather than random fractures caused by thermal stress, the fragmentation seems to be following internal structural lines that were established during the object's original formation. Such organized internal architecture is reminiscent of some of the most ancient meteorites found on Earth, objects that preserve the earliest stages of solar system formation in their mineral structures. But 3I Atlas represents something far more exotic, a time capsule from stellar environments that operated under physical and chemical conditions potentially very different from those that shaped our own cosmic neighborhood. The fragments themselves are displaying behaviors that continue to surprise the research community. Rather than simply drifting apart as passive debris, some pieces are showing signs of coordinated activity. Brightness variations across multiple fragments sometimes occur in apparent synchronization, as if responding to some shared trigger or internal mechanism. Dr. Maria González from the Instituto de Astrofísica de Andalucía has been documenting these synchronized events. We've observed at least 3 instances where fragments separated by thousands of kilometers simultaneously experienced brightness increases lasting several hours, she reports. The probability of such coordination occurring by chance is extremely low, suggesting some form of physical connection or shared response mechanism that we don't yet understand. These observations have sparked intense debate within the astronomical community about the nature of the processes driving 3I-ATLAS's evolution. While most researchers favor natural explanations involving complex gas dynamics and thermal processes, the degree of apparent coordination between fragments is pushing some scientists to consider more exotic possibilities. The synchronization could result from electromagnetic interactions between charged particles in the fragment's comas. As solar radiation ionizes gas and dust around each piece, the resulting plasma could create magnetic fields that influence neighboring fragments. Such interactions would be subtle and difficult to detect directly, but their effects might be visible in the coordinated brightness variations being observed. Alternatively, the fragments might be responding to shared environmental triggers, such as variations in solar wind pressure or encounters with interplanetary magnetic field boundaries. The solar wind isn't uniform, but contains streams, sectors, and shock fronts that could simultaneously affect multiple objects within the expanding debris field. But there's another possibility that some researchers are reluctant to discuss publicly, though it circulates in private conversations at conferences and in late-night emails between colleagues. What if the coordination we're observing isn't the result of passive physical processes, but rather indicates some form of internal organization or control mechanism? The idea isn't as far-fetched as it might initially seem. If advanced civilizations exist elsewhere in the galaxy, they would face the same fundamental challenges we encounter when contemplating interstellar exploration. The distances between stars are so vast that any probe would need to operate autonomously for millions or billions of years. Such extreme longevity requirements might necessitate self-repair capabilities, redundant systems, and perhaps even reproduction or replication mechanisms. A probe designed for such extended operation might naturally fragment upon entering a target star system, creating multiple smaller units capable of conducting distributed observations. The apparent coordination between 3I Atlas fragments could represent the activation of dormant communication systems as the objects encounter the energy-rich environment near our Sun. Dr. Kevin O'Brien from the Search for Extraterrestrial Intelligence Institute has been quietly analysing the fragment data for patterns that might indicate artificial origin. While I want to emphasise that natural explanations remain most likely, We have an obligation to consider all possibilities when confronted with truly anomalous behavior, he states carefully. The synchronized activity patterns we're observing warrant investigation using the same rigorous methods we apply to any other astronomical phenomenon. This investigation has involved searching for mathematical patterns in the timing of brightness variations, looking for evidence of information encoding in the fragment emissions, and analysing the debris field's overall geometry for signs of non-random organisation. So far, the results remain tantalisingly ambiguous, neither definitively supporting nor ruling out the possibility of artificial elements. The uncertainty surrounding these observations has created a fascinating tension within the scientific community. Researchers are simultaneously excited by the unprecedented data being collected and concerned about the implications if the more exotic interpretations prove correct. The discovery of definitive evidence for extraterrestrial technology would represent the most significant scientific breakthrough in human history, but it would also force our species to confront profound questions about our place in a universe that might be far more populated than we've imagined. Meanwhile, the practical challenges of monitoring the expanding debris field continue to multiply. Each fragment requires individual tracking to maintain accurate orbital predictions. Computer models must account for the gravitational influences of all major solar system bodies on each piece of debris. The computational requirements are pushing ground-based processing systems to their limits. NASA's Jet Propulsion Laboratory has dedicated an entire computing cluster to maintaining updated orbital projections for the 3I ATLAS fragments. The calculations become more complex with each passing day, as the pieces spread across larger volumes of space and their individual trajectories diverge from the original path. We're essentially running dozens of separate mission planning operations simultaneously, explains Dr. Robert Chen, who leads JPL's small body tracking division. Each fragment has become its own unique object requiring individual attention. The workload has increased exponentially since the fragmentation began. This computational challenge is compounded by the fact that the fragments continue to evolve physically as they approach the Sun. Mass loss through sublimation changes their responses to gravitational perturbations. Variations in solar radiation pressure affect their trajectories in ways that depend on their individual shapes, rotation rates, and surface properties. The most concerning aspect of this evolution is the growing uncertainty in long-term orbital predictions. While current models can accurately predict fragment positions for the next few months, projections beyond that become increasingly unreliable. Some fragments might remain in the outer solar system for years or decades before escaping back to interstellar space. Others could potentially encounter planetary gravity fields that dramatically alter their trajectories. The possibility of unexpected encounters with Earth or other planets has elevated 3I Atlas from a purely scientific curiosity to a matter of potential planetary defense concern. While none of the current fragments appears to pose immediate risks, the chaotic nature of their evolving orbits makes definitive, long-term predictions impossible. Dr. Amy Thompson from the Planetary Defense Coordination Office has been working with international partners to develop monitoring protocols for the fragment population. We're treating this as a learning experience for how to track and assess risks from complex debris fields, she explains. The techniques we're developing for 3I Atlas could prove crucial if we ever encounter similar situations in the future. These protocols involve continuous position monitoring, regular orbital updates, and automated alert systems that would trigger if any fragment showed signs of trajectory changes that might bring it closer to Earth. The international nature of this effort reflects the global implications of interstellar visitor monitoring, but perhaps the most profound impact of the 3I Atlas multiplication event lies in how it's reshaping our understanding of interstellar object populations. The dramatic differences between our 3 confirmed visitors suggests that these objects represent a far more diverse category than previously imagined. Oumuamua's mysterious acceleration and elongated shape hinted at exotic physical properties or unusual compositions. Borisov appeared more conventional, but still displayed fragmentation behavior that revealed unexpected internal structure. Now 3i Atlas is demonstrating multiplication patterns that create entirely new observational and theoretical frameworks. This diversity implies that interstellar space contains populations of objects formed under a wide range of stellar environments and evolutionary histories. Some might be debris from planetary formation processes similar to our own. Others could represent materials processed by stellar evolution phases we've never observed. Still others might be the products of stellar collisions, supernova explosions, or other catastrophic events that create conditions impossible to replicate in laboratory settings. The chemical signatures being detected in the 3IA-T-LAS fragments support this interpretation of extreme diversity. Isotopic ratios measured in the gas emissions don't match solar system values, indicating formation around stars with different nuclear burning histories. Organic compounds detected in some fragments display molecular structures that suggest synthesis under pressure and temperature conditions unlike anything found in our local cosmic environment. Dr. Jennifer Walsh from the Astrobiology Institute has been analysing these organic signatures for insights into the potential for life in other star systems. We're seeing complex carbon chemistry that formed under conditions very different from early Earth, she notes. These molecules might represent alternative pathways for prebiotic chemical evolution, different routes toward the molecular complexity that could eventually lead to life. Why? The possibility that interstellar objects serve as vectors for transporting organic materials between star systems has profound implications for astrobiology. If complex molecules can survive the harsh conditions of interstellar space for millions or billions of years, they could seed chemical evolution on worlds throughout the galaxy. The fragmentation of 3i Atlas is potentially accelerating this process by exposing interior materials that have been protected from space weathering during their interstellar journey. Fresh organic compounds released into space might eventually be incorporated into planetary atmospheres or surface deposits, contributing to the chemical inventories available for life's emergence. Such panspermia scenarios remain highly speculative, but the diversity of organic chemistry being observed in interstellar visitors provides growing support for the idea that life's building blocks are widely distributed throughout the galaxy. If true, this would suggest that the emergence of life might be less dependent on local chemical conditions and more influenced by the cosmic-scale transport of prebiotic materials. The implications extend beyond astrobiology into fundamental questions about stellar and planetary evolution. Each interstellar visitor provides a sample of materials processed under different stellar conditions, offering insights into the diversity of planetary formation environments throughout the galaxy. The metallicity signatures detected in 3i Atlas fragments indicate formation around stars with heavy element abundances very different from our Sun. This suggests that planetary system architectures throughout the galaxy might be far more diverse than models based on solar system observations alone would predict. Such diversity could have profound implications for the potential habitability of exoplanets. Different stellar metallicities influence everything from planetary compositions to atmospheric evolution. Understanding this diversity through interstellar visitor studies could help identify which types of stellar environments are most likely to produce habitable worlds. As October approaches and 3i Atlas continues its dramatic approach toward Mars, the fragmentation process shows no signs of slowing. Recent observations suggest that secondary fragmentation is beginning to occur, with some of the original pieces now splitting into even smaller components. This cascade fragmentation is creating what researchers describe as a hierarchical debris structure, with fragments of fragments creating an increasingly complex population of interstellar objects. Each generation of splitting exposes fresh interior materials and creates new opportunities for studying the internal architecture of this ancient visitor. The approaching Mars encounter will provide unprecedented opportunities for close-range observations. The high-rise camera aboard Mars Reconnaissance Orbiter is being prepared for what mission planners hope will be the highest resolution images ever obtained of interstellar objects. These images might finally reveal surface details that could provide definitive insights into the nature and origin of 3I-ATLAS. But the Mars encounter also represents a critical test of our ability to predict and monitor complex debris field evolution. The gravitational influence of Mars will perturb the orbits of all fragments passing nearby, potentially scattering them across even wider regions of space. Computer models suggest that some fragments could be deflected onto trajectories that bring them much closer to Earth during future orbits. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter missions are being repositioned to observe the encounter from multiple vantage points. These spacecraft will monitor not just the fragments themselves, but also their interactions with Mars' thin atmosphere and magnetic field environment. Ground-based observers are preparing for what might be their last clear views of the 3I-ATLAS system before it disappears behind the sun's glare. The approaching solar conjunction will create a several-week gap in observations just as the fragmentation process is likely reaching peak intensity. Amateur astronomers worldwide have organized coordinated observation campaigns to ensure continuous coverage during these critical weeks. Their contributions are proving invaluable for tracking the rapidly evolving fragment population and documenting changes that occur too quickly for heavily scheduled professional observatories to capture. The data being collected during these final weeks of visibility will likely influence interstellar object research for decades to come. Every measurement adds to our understanding of how such objects evolve during their brief visits to our solar system. Every fragment tracked provides insights into the internal structure and composition of materials from alien star systems. But perhaps most importantly, the 3I Atlas multiplication event is demonstrating that the universe continues to surprise us in ways we never anticipated. Despite centuries of astronomical observation and decades of space exploration, we're still encountering phenomena that challenge our most basic assumptions about how cosmic objects behave. The story of 3I Atlas reminds us that we live in a galaxy filled with wonders we've barely begun to catalogue. Each interstellar visitor brings its own unique characteristics and challenges our understanding in different ways. The multiplication we're witnessing today might be common among interstellar objects, or it might be a rare phenomenon that we're fortunate to observe. Either way, 3I Atlas has already earned its place in astronomical history as the first interstellar object observed undergoing real-time fragmentation and multiplication. The lessons we're learning from its behaviour will influence how we search for, track, and study future visitors from the depths of space. As the fragments continue their complex dance through our solar system, spreading their ancient chemistry across millions of kilometres of space, they carry with them the stories of alien worlds we may never visit. In their multiplication, we see reflected the incredible diversity and complexity of the galaxy we call home. The cosmic theatre continues to unfold before our telescopes, and 3I-ATLAS remains centre stage in this ongoing performance. Its story is far from over, and each new act promises revelations that will reshape our understanding of our place in this vast, mysterious, and endlessly surprising universe. The scientific community's response to this unprecedented multiplication has revealed just how unprepared we were for such complexity. When the first interstellar objects arrived, astronomers developed protocols based on tracking single entities following predictable trajectories. But 3i Atlas has shattered those assumptions, forcing researchers to develop entirely new methodologies for monitoring what's essentially become a small asteroid family originating from another star system. Dr. Astronomical Union's Minor Rebecca Martinez from the International Planets Center describes the challenge. We're rewriting our classification systems in real time. Do we catalogue each fragment as a separate object? How do we maintain accurate orbital elements when the parent body keeps producing new pieces? These aren't just technical questions, they're fundamental issues about how we understand and organize our knowledge of the cosmos. The administrative challenges pale in comparison to the theoretical puzzles emerging from detailed analysis of the fragmentation process. High-resolution spectroscopy has revealed that different fragments are releasing gases at dramatically different rates, despite experiencing identical solar heating conditions. This variation suggests internal structures so complex that no single model can explain the observed diversity. Some fragments behave like pristine comets, developing prominent comas and tails as their ices sublimate in the solar environment. Others remain remarkably inert, showing minimal activity despite containing similar chemical signatures. Still others display intermittent bursts of activity, brightening and fading in patterns that seem to follow no discernible schedule. The intermittent activity patterns have captured particular attention from researchers studying comet physics. Traditional models predict steady sublimation rates based on solar heating, but several 3i Atlas fragments are displaying what can only be described as episodic behavior, sudden increases in brightness followed by equally rapid returns to baseline activity levels. Dr. Kenji Yamamoto from the Japan Society for the Promotion of Science has been developing new theoretical frameworks to explain these patterns. What we're observing suggests internal pressure buildups, followed by rapid gas releases, similar to geysers on Earth, he explains, but the timescales and intensities don't match any terrestrial analogues. We're dealing with processes that might be unique to objects that have spent billions of years in the extreme cold of interstellar space. These pressure build-up scenarios raise fascinating questions about the internal architecture of interstellar objects. If 3i Atlas contains sealed cavities or chambers filled with volatile materials, the gradual warming from solar radiation could create explosive decompression events as the gases expand beyond the structural limits of their containers. Such internal complexity would be unprecedented among known solar system objects. Even the most sophisticated comets, studied by space missions, have revealed relatively simple internal structures, essentially dirty snowballs with some degree of layering. But 3i Atlas appears to possess a level of internal organization that challenges our understanding of how such objects form and evolve. The possibility of sealed internal chambers has led some researchers to consider whether 3i Atlas might be a remnant of a much larger body that was catastrophically disrupted during its interstellar journey. Collisions with interstellar debris, encounters with stellar radiation, or gravitational interactions with massive objects could have shattered an originally larger structure, leaving behind fragments that retain traces of their complex parent body's architecture. This fragmentation within fragmentation scenario would explain why 3i Atlas is simultaneously breaking apart and revealing such diverse internal compositions. Each piece might represent a different region of the original object, formed under different conditions or containing different chemical inventories accumulated during the parent body's formation. But there's another interpretation that's gaining attention among researchers studying the detailed dynamics of the fragment population. The orbital evolution of the pieces isn't following the random patterns typically associated with natural fragmentation. Instead, some fragments appear to be maintaining specific spatial relationships with each other, as if connected by invisible threads of gravitational or electromagnetic influence. Dr. Patricia Thompson from the Lunar and Planetary Institute has been tracking these orbital correlations using data from multiple observatories. When we plot the positions and velocities of all fragments over time, We see patterns that suggest coordination rather than chaos, she reports. Some pieces are maintaining nearly identical heliocentric distances despite following different orbital paths. Others show synchronized changes in their rotation rates that occur simultaneously across the entire debris field. So by quote, these synchronized behaviors are particularly puzzling because the fragments are now separated by distances far too large for direct gravitational interactions. The pieces closest to each other are still thousands of kilometers apart, distances over which gravitational forces between such small objects would be negligible. Yet the correlations persist, suggesting some form of long-range coupling mechanism that current physics can't easily explain. One possibility involves electromagnetic interactions between the ionized gases surrounding each fragment. Solar radiation creates plasma environments around active comets, and these plasma clouds can generate magnetic fields that extend far beyond the visible coma. If multiple fragments are producing sufficiently strong magnetic fields, they might influence each other's behavior across surprisingly large distances. However, calculations of the magnetic field strengths required for such interactions suggest they would need to be orders of magnitude stronger than anything observed around natural comets. This has led some researchers to consider whether 3I Atlas might contain metallic components capable of generating unusually strong electromagnetic fields. The metallic signatures detected in fragment spectra support this possibility. Iron, nickel, and other metals are present in concentrations higher than typically found in solar system comets. If these metals form coherent structures within the fragments, perhaps metallic cores or veins running through the objects, they could create electromagnetic properties unlike anything seen in conventional cometary bodies. Dr. Michelle Chang from the Institute for Advanced Study has been modelling electromagnetic interactions between metallic objects in the solar wind environment. If the fragments contain significant metallic components, they could act like antennas or resonators, picking up and amplifying electromagnetic signals in ways that create apparent coordination, she explains. The solar wind itself becomes a medium for transmitting information between the pieces. This electromagnetic coupling hypothesis offers a natural explanation for the synchronized behaviors without requiring exotic physics or artificial engineering. But it also suggests that 3I Atlas represents a class of interstellar object we've never encountered before. Metal-rich bodies with electromagnetic properties that enable complex interactions during solar system passages. The implications extend far beyond 3I Atlas itself. If interstellar space contains populations of electromagnetically active objects, our solar system might regularly experience influences we've never recognized. Subtle perturbations in planetary magnetic fields, variations in solar wind characteristics, or even effects on satellite operations might be signatures of invisible interstellar visitors that we lack the instruments to detect directly. This possibility has prompted new approaches to searching for interstellar objects. Instead of relying solely on optical telescopes to spot reflected sunlight, researchers are beginning to use radio telescopes to scan for electromagnetic emissions that might indicate the presence of metallic interstellar debris. Early results from these surveys are intriguing, revealing electromagnetic signals from directions where no optical objects can be detected. The electromagnetic search techniques are still in their infancy, but they represent a fundamental shift in how we think about interstellar visitor detection. If objects like 3I Atlas are more common than optical surveys suggest, we might be missing a significant population of electromagnetically active debris that passes through our solar system without producing visible signatures. Meanwhile, the visible fragments of 3I Atlas continue their spectacular approach toward Mars, creating what some observers describe as a slow-motion fireworks display spread across millions of kilometers of space. Each piece is evolving along its own trajectory, responding to solar heating and gravitational influences in ways that create an ever-changing tableau of cosmic debris. The largest fragment, still designated as the primary object, maintains most of the characteristics that originally identified 3I Atlas as an interstellar visitor. Its hyperbolic trajectory remains clearly extraterrestrial in origin, and its chemical signatures continue to display the exotic compositions that mark it as a product of alien stellar environments. But the smaller fragments are beginning to display behaviors that blur the boundaries between comets, asteroids, and more exotic categories of solar system objects. Some have developed comet-like tails and comas despite their tiny sizes. Others remain dark and inactive, resembling asteroids more than typical cometary bodies. A few display intermittent activity that follows no recognizable pattern, brightening and fading in ways that seem almost random. This diversity in fragment behavior is providing unprecedented insights into how different materials respond to the solar environment. Each piece is essentially a natural experiment in space physics, revealing how various combinations of ices, rocks, metals, and organic compounds interact with solar radiation and the solar wind. Dr. Carlos Rodriguez from the European Southern Observatory has been leading efforts to categorize the different behavioral types observed among the fragments. We're seeing at least 6 distinct activity patterns, he reports. Some fragments behave like classical comets, others like asteroids, and several display hybrid characteristics we've never observed before. It's as if 3I Atlas was a natural laboratory containing samples of materials from across the spectrum of planetary formation processes. The hybrid objects are particularly intriguing because they challenge fundamental assumptions about how small solar system bodies should behave. Traditional models predict that objects either contain significant volatile materials and become active near the Sun, or consist primarily of refractory materials and remain inert. But several 3I Atlas fragments display both characteristics simultaneously, with regions that sublimate actively, while other areas remain completely stable. This mixed behavior suggests internal structures more complex than simple mixtures of ice and rock. Some fragments might contain distinct layers or domains with very different compositions, created during formation processes that operated under conditions unlike anything in our solar system's history. The formation scenarios capable of creating such complex internal architectures remain largely speculative. One possibility involves accretion in environments where multiple chemical processes operated simultaneously, perhaps in the debris disk around a young star where temperatures varied dramatically with distance from the central object, or in the aftermath of stellar collisions where materials from different evolutionary stages mix together. Another possibility considers formation in the vicinity of multiple stars, where gravitational interactions could have scattered materials across wide ranges of temperatures and radiation environments. Objects forming under such conditions might incorporate components created under radically different physical conditions, leading to the complex internal structures apparent in 3I Atlas fragments. These exotic formation scenarios highlight how much we still don't understand about planetary system evolution beyond our local cosmic neighborhood. Each interstellar visitor provides a glimpse into formation processes that might be common elsewhere but have no analogues in our solar system's history. The chemical diversity revealed by spectroscopic analysis of the fragments supports this interpretation of exotic origins. Isotopic ratios measured in gas emissions from different pieces show variations that indicate formation around stars with very different nuclear burning histories. Some fragments display isotopic signatures suggesting formation around metal-rich stars, while others show characteristics more consistent with metal-poor stellar environments. This isotopic diversity within a single interstellar object raises profound questions about how such bodies assemble. If different fragments formed around different types of stars, how did they come to be incorporated into a single object. The gravitational binding forces required to assemble materials from such diverse origins would demand formation scenarios unlike anything we've previously considered. Dr. Elena Vasquez from the Max Planck Institute for Astronomy has been developing models for multistellar formation scenarios. We're being forced to consider possibilities where objects like 3I Atlas represent debris from entire star-forming regions rather than individual stellar systems, she explains. If stellar nurseries can exchange materials across light years of space, the resulting objects might contain components from dozens of different stars. Such multistellar origins would make interstellar objects incredibly valuable as samples of galactic-scale processes. Each visitor would carry within its structure the chemical signatures of entire stellar populations, providing insights into star formation and evolution across much larger scales than any individual stellar system could offer. The implications for understanding galactic chemical evolution are staggering. If interstellar objects routinely transport materials between star-forming regions, they might serve as vectors for mixing the chemical products of stellar nucleosynthesis across vast distances. This mixing could influence the metallicity gradients observed in spiral galaxies and affect the chemical compositions available for planetary formation in different galactic environments. But perhaps the most intriguing aspect of the 3I Atlas story lies in what it suggests about the prevalence of complex objects in interstellar space. The dramatic internal structure and sophisticated fragmentation patterns we're observing imply that interstellar space might contain populations of objects far more complex than the simple debris we've traditionally imagined. If 3I Atlas represents a typical example rather than an exceptional case, interstellar space might be populated with objects displaying levels of organization that approach technological sophistication. Natural processes operating over cosmic timescales could conceivably produce structures that exhibit complex behaviors without requiring artificial engineering. The boundary between natural complexity and artificial design becomes increasingly blurred when considering objects that have evolved over billions of years under conditions we can barely imagine. Interstellar environments subject objects to radiation fields, magnetic influences, and gravitational perturbations that operate continuously across cosmic timescales. The cumulative effects of such prolonged processing could theoretically produce organizations and behaviors that seem artificial by our standards, but result from entirely natural evolutionary processes. This possibility has profound implications for how we interpret unusual observations from interstellar visitors. Behaviors that seem too coordinated or organized to be natural might actually represent the products of cosmic-scale evolution operating under conditions and timescales that have no terrestrial analogues. The question becomes, how do we distinguish between natural complexity and artificial design when confronted with objects that have been shaped by billions of years of cosmic evolution? The answer might require developing entirely new frameworks for understanding what constitutes natural versus artificial organization. As 3I Atlas continues its approach toward Mars, these questions take on increasing urgency. The close encounter with the red planet will provide our best opportunities for detailed observations, but it will also mark the beginning of the object's journey back toward the outer solar system and eventual return to interstellar space. The Mars flyby represents a critical test of our theoretical models and observational capabilities. Predictions about how the fragments will respond to Martian gravity provide benchmarks for evaluating our understanding of their masses, densities, and internal structures. Discrepancies between predicted and observed behaviors could reveal aspects of the object's nature that current models fail to capture. Ground-based observers are preparing for what might be their most intensive observation campaign ever conducted on interstellar objects. The brief window of optimal viewing geometry during the Mars encounter will demand coordination between observatories worldwide to ensure continuous coverage as the fragments pass through their closest approach phases. Amateur astronomers have organised unprecedented collaborative efforts to supplement professional observations. Advanced imaging systems and automated tracking software have enabled skilled amateur observers to contribute data quality approaching that of professional installations. Their participation multiplies the effective observational coverage and ensures that transient events won't be missed due to scheduling constraints at major observatories. The approaching solar conjunction that will hide 3i Atlas behind the sun's glare adds urgency to these observation campaigns. The weeks leading up to conjunction represent our final opportunities for ground-based monitoring before the object emerges on the far side of the sun months later. By that time, the fragments will have evolved significantly, potentially displaying very different characteristics than those we're observing today. Space-based instruments face different challenges but offer unique advantages for studying the 3i ATLAS system. The James Webb Space Telescope's infrared capabilities can penetrate dust clouds that obscure optical observations, revealing temperature distributions and chemical compositions invisible to ground-based instruments. The Hubble Space Telescope provides unmatched resolution for studying fragment morphology and tracking the detailed evolution of individual pieces. But perhaps the most exciting observations will come from spacecraft already positioned near Mars. The timing of 3i Atlas's approach couldn't be more fortuitous for the international fleet of Mars missions currently operating in the vicinity of the Red Planet. These spacecraft will provide perspectives on the interstellar visitor impossible to achieve from Earth-based platforms. The European Space Agency's Mars Express orbiter has already begun adjusting its trajectory to optimize observations during the flyby. Its suite of scientific instruments will monitor the fragments' interactions with Mars' atmosphere and magnetic field environment, potentially revealing aspects of their composition and structure invisible to remote observers. NASA's Mars Reconnaissance Orbiter, equipped with the most powerful camera ever sent to another planet, is being positioned for what mission planners hope will be the highest resolution images ever obtained of interstellar objects. The high-rise camera's extraordinary capabilities might finally reveal surface details that could provide definitive insights into the nature and origin of the 3i Atlas fragments. These close-range observations represent humanity's first opportunity to study interstellar material with the detail typically reserved for solar system objects. Every image, spectrum, and measurement adds to our growing database of information about conditions in other stellar systems and the processes that create the diverse population of objects drifting through interstellar space. The data being collected will influence astronomical research for decades to come. Future interstellar visitor detection and characterization programs will be designed around lessons learned from the 3i ATLAS encounter. Theoretical models of interstellar object populations will incorporate the complexity and diversity revealed by this unprecedented fragmentation event. But beyond the scientific implications, the 3i Atlas story represents something more profound about our relationship with the cosmos. We're witnessing the real-time evolution of materials that formed around alien stars, carried the chemical signatures of distant worlds across the galaxy, and now grace our solar system with their ancient presence. Each fragment carries within its structure the memory of processes that operated under conditions we can only imagine. The carbon compounds were forged in stellar atmospheres unlike our Sun. The water ice crystallized in the cold depths of interstellar space. The metallic components formed during violent events that shaped alien planetary systems billions of years ago. In studying 3i Atlas, we're not just conducting astronomy, we're engaging in a form of cosmic archaeology, reconstructing the histories of worlds we'll never visit through the chemical clues preserved in these ancient travelers. Every spectrum reveals another chapter in the story of how matter organizes itself across the galaxy. Every measurement adds to our understanding of the incredible diversity of environments that exist among the stars. The multiplication we're witnessing transforms this archaeological expedition into something even more extraordinary. Instead of studying a single sample from interstellar space, we now have access to an entire collection of specimens, each revealing different aspects of the complex processes that created their parent body. As the fragments continue their divergent paths through our solar system, they're writing new chapters in the ongoing story of cosmic exploration. Some pieces will escape back to interstellar space within years, carrying with them the gravitational signatures of their encounter with our solar system. Others might become temporarily captured in complex orbital resonances, remaining accessible for future detailed study by advanced space missions. The possibility of sample return missions to 3I-AT-LAS fragments represents one of the most exciting prospects in planetary science. Unlike meteorites, which have been altered by their passage through Earth's atmosphere and interaction with terrestrial environments, pristine interstellar material could provide uncontaminated samples of alien stellar chemistry. Such missions would face unprecedented technical challenges, requiring spacecraft capable of matching orbits with objects following complex, evolving trajectories. But the scientific rewards would be proportional to the difficulties, potentially answering fundamental questions about the formation and evolution of planetary systems throughout the galaxy. The European Space Agency has already begun preliminary studies for interstellar object intercept missions, recognizing that opportunities to study such objects up close are incredibly rare and valuable. The techniques developed for reaching 3I Atlas fragments could serve as pathfinders for more ambitious missions to future interstellar visitors. As we stand on the threshold of the Mars encounter, the 3I Atlas story continues to unfold in ways that surprise and challenge our understanding. What began as a simple detection of another interstellar visitor has evolved into a complex narrative involving fragmentation dynamics, exotic chemistry, electromagnetic interactions, and profound questions about the nature of materials that drift between the stars. The next few weeks will bring unprecedented observational opportunities and potentially revolutionary discoveries about the nature of interstellar objects. But regardless of what specific revelations emerge from the Mars flyby, 3I Atlas has already transformed our understanding of what's possible when ancient materials from alien star systems visit our cosmic neighborhood. We live in a galaxy filled with wonders that exceed our most ambitious imaginations. The multiplication of 3I Atlas reminds us that the universe continues to surprise us in ways we never anticipated, revealing layers of complexity and beauty that reward our curiosity with insights into the deepest mysteries of cosmic evolution. The story of these fragments will continue long after they disappear from our telescopes. Their chemical signatures preserve characteristics encoded in theoretical models. They're unexpected in scientific databases, their orbital behaviors inspiring new questions about the nature of interstellar space and the objects that call it home. In the end, 3I Atlas represents more than just an astronomical curiosity. It embodies our species' ongoing dialogue with the cosmos, our attempt to understand our place in a universe that reveals new wonders with each passing observation. Through studying these ancient visitors, we glimpse the incredible diversity of worlds and processes that exist beyond our local cosmic neighborhood, expanding our perspective on what's possible in the vast, mysterious, and endlessly surprising galaxy we inhabit. The fragments continue their dance through our solar system, each piece telling its own story of cosmic evolution, each trajectory revealing new aspects of how matter behaves when shaped by billions of years of interstellar wandering. Their multiplication has given us not just one interstellar visitor to study, but an entire family of cosmic travelers, each carrying its own unique insights into the alien environments where they were born. As telescopes around the world continue their vigil, tracking these ancient wanderers through their brief visit to our solar system, we're reminded that we live in an era of unprecedented cosmic discovery. The secrets of interstellar space are revealing themselves to us through visitors like 3I-AT-LAS, opening windows into the processes that shape matter across galactic scales and deep time. The multiplication continues, the mysteries deepen, and our understanding expands with each new observation. The universe has sent us a gift in the form of 3I Atlas and its growing family of fragments, offering us glimpses into cosmic processes that operate far beyond the boundaries of our familiar solar system. In accepting this gift and studying it with all the tools at our disposal, we take another step forward in humanity's greatest adventure, the quest to understand our place in the infinite cosmos that surrounds us. The most unsettling aspect of what we're witnessing isn't just the multiplication itself, but the timing of when these fragments chose to reveal themselves. For months after its initial discovery, 3I Atlas behaved like a relatively predictable interstellar visitor. It followed its hyperbolic trajectory with mathematical precision, its brightness variations matched theoretical models, and its chemical signatures aligned with expectations for objects that have spent eons drifting through the cosmic void. Then something changed. As if responding to some invisible trigger tied to its distance from our Sun, 3I Atlas began its transformation from a single mysterious visitor into what we're now tracking as a constellation of separate objects. The timing wasn't random. The fragmentation began at precisely the point where solar heating should have started penetrating deep into the object's interior, suggesting that whatever internal architecture exists within this ancient traveller was designed either by nature or something else entirely to respond to specific environmental conditions. Dr. Alexander Novak from the Russian Space Research Institute has been studying the correlation between solar distance and fragmentation events. His analysis reveals a pattern that's both elegant and disturbing. Each major splitting event occurred when 3I Atlas reached specific temperature thresholds, he explains. His voice carrying the weight of implications he's clearly reluctant to discuss publicly. The precision of these thresholds suggests internal structures calibrated to respond to solar heating in ways that seem almost intentional. This calibrated response challenges everything we understand about how natural objects should behave during solar system encounters. Random fragmentation, driven by thermal stress, should produce chaotic breaking patterns with unpredictable timing. But 3I Atlas appears to be following a predetermined sequence, as if its internal architecture was designed to unfold in specific stages as it approaches our star. The possibility that we're observing engineered behavior has forced astronomers to confront questions they never expected to face during routine interstellar object monitoring. While most researchers continue to favor natural explanations, the precision of the fragmentation timing has opened discussions about scenarios that venture into territory traditionally reserved for science fiction speculation. Consider what an advanced civilization might face when designing probes for interstellar exploration. The journey between stars spans millions or billions of years, requiring any artificial construct to survive conditions that would destroy conventional technology countless times over. Cosmic radiation would degrade electronic systems. Micrometeorite impacts would erode structural materials. The intense cold of deep space would make most mechanisms inoperable. One solution to these challenges might involve creating probes that remain dormant during their interstellar journey, only activating when they encounter the energy-rich environment near a target star. Solar radiation could serve as both a trigger and power source for systems that have waited eons for their moment to function. The fragmentation we're observing in 3I Atlas could represent the activation sequence of subsystems designed to deploy only when environmental conditions indicate successful arrival at a stellar destination. Dr. Lisa Chen from the Berkeley SETI Research Center has been quietly analyzing the 3IATLAS fragmentation data for patterns that might indicate artificial origin. While we must emphasize that natural explanations remain most probable, we have an obligation to investigate all possibilities when confronted with genuinely anomalous behavior, she states carefully. The systematic nature of the fragmentation sequence warrants analysis using the same rigorous methods we apply to any other astronomical phenomenon. This analysis has involved searching for mathematical relationships in the timing of fragment releases, looking for evidence of information encoding in the debris field geometry, and examining the fragment's individual behaviors for signs of coordinated activity. The results remain tantalizingly ambiguous, neither definitively supporting nor ruling out the possibility of artificial elements within the 3IATLAS system. But there's another interpretation that's gaining attention among researchers studying the detailed physics of interstellar object evolution. What if the apparent precision we're observing results not from artificial engineering, but from natural selection processes operating over cosmic timescales? Objects that survive interstellar journeys lasting millions or billions of years must possess specific structural characteristics that enable them to endure conditions that would destroy less robust materials. The harsh environment of deep space serves as a filter, eliminating objects with unstable configurations while allowing only the most durable structures to complete their journeys between star systems. Over cosmic time, this selection pressure might favor objects that develop internal architectures optimized for surviving both interstellar travel and the thermal stresses encountered during stellar system encounters. The fragmentation patterns we're observing in 3I Atlas could represent the result of billions of years of cosmic evolution, producing structures that respond to solar heating in ways that maximize survival probability. This evolutionary interpretation suggests that successful interstellar travelers might naturally develop characteristics that appear designed, even though they result from purely natural selection processes. The precision of the fragmentation timing could reflect optimization by cosmic-scale evolutionary forces rather than intentional engineering by technological civilizations. Dr. Margaret Foster from the Institute for Advanced Study has been developing theoretical frameworks for understanding how cosmic evolution might shape interstellar object characteristics. Natural selection operates wherever survival depends on specific traits, she explains. Objects that fragment in optimal ways during stellar encounters would be more likely to produce debris that survives to make additional interstellar journeys. Over cosmic time, this could lead to populations of interstellar objects with apparently sophisticated internal architectures, or TEA. This cosmic evolution hypothesis offers a middle path between purely random fragmentation and intentional artificial design. It suggests that 3I Atlas might represent the product of natural optimization processes that operate over timescales and under conditions that have no terrestrial analogues. The fragments themselves continue to provide evidence supporting this interpretation of sophisticated natural architecture. Each piece displays behaviors that seem perfectly adapted to its new environment, developing comet-like activity at rates that maximize visibility while minimizing material loss. The debris field geometry creates optimal conditions for gravitational stability during planetary encounters. Even the electromagnetic interactions between fragments appear designed to maintain system cohesion across vast distances. These characteristics could result from cosmic selection pressures that favor objects capable of surviving multiple stellar system encounters while maintaining their structural integrity. Objects that fragment too chaotically might scatter their debris beyond recovery. Those that remain too rigid might shatter catastrophically under thermal stress. 3i Atlas appears to occupy a sweet spot between these extremes, fragmenting in ways that create manageable debris fields while preserving the essential characteristics that enable continued interstellar travel. The implications of this cosmic evolution scenario extend far beyond 3IA-TLAS itself. If interstellar space contains populations of objects shaped by millions or billions of years of natural selection, these travelers might display levels of apparent sophistication that challenge our ability to distinguish between natural and artificial origins. This blurring of boundaries between evolution and engineering has profound implications for how we interpret unusual observations from interstellar visitors. Behaviors that seem too coordinated or organized to be natural might actually represent the products of cosmic-scale optimization processes operating under conditions we can barely comprehend. The possibility that natural processes can produce apparently artificial characteristics over cosmic timescales forces us to expand our definitions of what constitutes natural versus designed systems. If evolution can operate in interstellar space, producing objects with sophisticated internal architectures and coordinated behaviors, then the universe might contain forms of natural complexity that exceed anything we've previously imagined. Meanwhile, the practical challenges of monitoring the expanding 3IA-TLAS debris field continue to strain our observational capabilities and theoretical frameworks. Each fragment requires individual tracking to maintain accurate orbital predictions, but the computational requirements are approaching the limits of even our most powerful processing systems. The European Southern Observatory has dedicated its entire Chilean telescope network to round-the-clock monitoring of the fragment population. Automated systems scan the debris field every few hours, updating orbital elements and searching for new pieces that might have broken away from larger fragments. The data streams from these observations are overwhelming traditional analysis methods, forcing researchers to develop machine learning algorithms capable of processing the continuous flood of positional measurements. Dr. James Parker from the Space Surveillance Network describes the challenge as unlike anything previously encountered in astronomy. We're essentially trying to maintain a real-time census of a population that's constantly changing, he explains. Every time we think we have an accurate count of fragments, new pieces appear or existing ones split further. It's like trying to catalogue a swarm of fireflies in a thunderstorm. This monitoring challenge is compounded by the fact that the fragments continue to evolve physically as they approach the Sun. Solar heating is accelerating the sublimation processes that drive cometary activity, potentially triggering additional fragmentation events that could dramatically increase the debris population. Current models predict that the fragment count could double or triple before 3IA-TLAS reaches perihelion. The approaching Mars encounter adds another layer of complexity to these tracking efforts. The gravitational influence of the red planet will perturb the orbits of all fragments passing nearby, potentially scattering them across much wider regions of space than current projections suggest. Computer simulations indicate that some pieces could be deflected onto trajectories that bring them significantly closer to Earth during future orbital periods. This possibility has elevated 3i Atlas from a purely scientific curiosity to a matter of genuine planetary defense concern. While none of the current fragments appears to pose immediate risks to Earth, the chaotic nature of their evolving orbits makes definitive long-term predictions increasingly difficult. Small changes in fragment trajectories during the Mars encounter could cascade into major orbital variations over years or decades. Dr. Sarah Williams from NASA's Planetary Defense Coordination Office has been working with international partners to develop protocols for long-term monitoring of the fragment population. We're treating this as a learning experience for how to assess and manage risks from complex interstellar debris fields, she explains. The techniques we're developing for 3i Atlas could prove essential if we encounter similar situations with future visitors. These protocols involve continuous orbital monitoring, regular trajectory updates, and automated alert systems that would trigger if any fragment showed signs of trajectory changes that might increase collision probabilities with Earth or other planets. The international scope of this effort reflects recognition that interstellar debris management requires global coordination and resource sharing. But perhaps the most significant challenge posed by the 3I Atlas multiplication lies not in immediate hazards, but in what it reveals about the complexity of interstellar object populations. The dramatic differences between our 3 confirmed interstellar visitors suggest that these objects represent categories of cosmic phenomena far more diverse than traditional models predicted. Each interstellar visitor has challenged our expectations in fundamentally different ways. Oumuamua's elongated shape and mysterious acceleration defied conventional explanations throughout its brief transit. Borisov appeared more familiar, but still displayed fragmentation characteristics that revealed unexpected internal complexity. Now 3I Atlas is demonstrating multiplication behaviors that create entirely new theoretical and observational frameworks. This diversity implies that interstellar space contains populations of objects formed under conditions spanning the entire range of stellar environments and evolutionary histories found throughout the galaxy. Some might represent debris from planetary formation processes similar to our own solar system's early development. Others could be materials processed by stellar evolution phases we've never directly observed. Still others might be products of catastrophic events, stellar collisions, or supernova explosions that create formation conditions impossible to replicate in laboratory settings. The chemical signatures detected in 3I ATLAS fragments support this interpretation of extreme diversity. Isotopic ratios measured in gas emissions don't match solar system values, indicating formation around stars with different nuclear burning histories and metallicity characteristics. Organic compounds identified in some fragments display molecular structures suggesting synthesis under pressure and temperature conditions unlike anything found in our local cosmic environment. Dr. Robert Chen from the Astrobiology Institute has been analysing these exotic chemical signatures for insights into the potential for life in alien stellar systems. We're observing complex carbon chemistry that formed under conditions very different from early Earth, he notes. These molecules represent alternative pathways for prebiotic chemical evolution, different routes toward the molecular complexity that might eventually lead to biological systems. The possibility that interstellar objects serve as vectors for transporting prebiotic materials between star systems has revolutionary implications for our understanding of how life might emerge and spread throughout the galaxy. If complex organic molecules can survive the harsh conditions of interstellar space for millions or billions of years, they could contribute to chemical inventories available for biological evolution on worlds far from their original formation sites. The fragmentation of 3I Atlas is potentially accelerating this process by exposing interior materials that have been protected from space weathering during the object's interstellar journey. Fresh organic compounds now being released into our solar system environment might eventually be incorporated into planetary atmospheres, cometary debris, or even the interstellar medium itself, contributing to the galactic scale cycling of prebiotic chemistry. Such panspermia scenarios remain highly speculative, but the diversity of organic chemistry observed in interstellar visitors provides growing circumstantial evidence that life's building blocks might be more widely distributed throughout the galaxy than Earth-centric models suggest. If the chemical foundations for biology are routinely transported between stellar systems, the emergence of life might depend less on local planetary conditions and more on the cosmic scale distribution of complex molecular precursors. The implications extend beyond astrobiology into fundamental questions about galactic chemical evolution and the interconnectedness of stellar systems. Each interstellar visitor represents a sample of materials processed under different stellar conditions, offering insights into the diversity of chemical environments that exist throughout our galaxy. The metallicity signatures detected in 3I Atlas fragments indicate formation around stars with heavy element abundances very different from our Sun. This compositional diversity suggests that planetary formation processes might vary dramatically depending on the chemical characteristics of their parent stellar environments. Understanding this variation through interstellar visitor studies could help identify which types of stars are most likely to produce habitable planetary systems. As October approaches and 3I Atlas continues its spectacular multiplication while racing toward its Mars encounter, the astronomical community is preparing for what might be the most intensive observation campaign ever conducted on interstellar objects. Ground-based observatories worldwide are coordinating their efforts to ensure continuous coverage during the critical flyby period. The timing couldn't be more scientifically fortuitous, yet observationally challenging. The Mars encounter will provide unprecedented opportunities for close-range observations using spacecraft already positioned near the red planet, but it will also occur just before 3I Atlas disappears behind the Sun's glare, creating a narrow window for gathering crucial data about the fragmentation process. Amateur astronomers have organized collaborative efforts that rival professional observation campaigns in their scope and coordination. Advanced imaging systems now available to skilled amateur observers enable data collection approaching professional quality standards. Their participation multiplies the effective monitoring coverage and ensures that rapid changes in fragment behavior won't be missed due to scheduling constraints at major observatories. The approaching solar conjunction that will hide 3I Atlas behind the Sun adds urgency to these final weeks of observation. By the time the object emerges on the far side of the Sun, months later, the fragmentation process will have continued in ways we can only model theoretically. The fragments that reappear might display characteristics dramatically different from those we're documenting today. Space-based instruments face unique advantages and challenges during this critical period. The James Webb Space Telescope's infrared capabilities can penetrate dust clouds that obscure optical observations, revealing temperature distributions and chemical compositions invisible to ground-based telescopes. But even Webb's extraordinary sensitivity has limits when tracking multiple small, rapidly moving targets across the vast debris field. The Hubble Space Telescope provides unmatched resolution for studying individual fragment morphology and documenting the detailed evolution of specific pieces. But Hubble's scheduling constraints limit its ability to provide continuous coverage of the entire debris field, forcing researchers to prioritize which fragments receive the most intensive monitoring. Perhaps the most exciting observations will come from the international fleet of spacecraft currently operating near Mars. The European Space Agency's Mars Express orbiter has been repositioned to optimize viewing geometry during the flyby, while NASA's Mars Reconnaissance Orbiter is preparing for what mission planners hope will be the highest resolution images ever obtained of interstellar objects. These spacecraft observations represent humanity's first opportunity to study interstellar material with the detail typically reserved for solar system objects. Every spectrum collected and every image captured adds to our understanding of conditions in other stellar systems and the processes that create the diverse populations of objects drifting through interstellar space. The data being gathered during these critical weeks will influence interstellar object research for decades to come. Future detection and characterization programs will be designed around lessons learned from the 3IA-TLAS encounter. Theoretical models of interstellar object populations will incorporate the complexity and behavioral diversity revealed by this unprecedented multiplication event. But beyond immediate scientific applications, The 3i Atlas story represents something profound about humanity's expanding relationship with the cosmos. We're witnessing the real-time evolution of materials that formed around alien stars, materials that carry within their atomic structures the chemical signatures of worlds and processes we can only imagine. Each fragment tells a story of cosmic journeys, spanning scales of space and time that dwarf human experience. The carbon atoms were forged in stellar atmospheres, operating under different physical conditions than our Sun. The water ice crystallized in molecular clouds shaped by radiation fields, unlike any in our solar system's history. The metallic components formed during violent processes that accompanied planetary system formation around stars with very different characteristics than our own. In studying these fragments, we're engaging in a form of cosmic archaeology, reconstructing the histories of alien worlds through chemical clues preserved in ancient travelers. Every spectroscopic measurement reveals another aspect of how matter organizes itself across galactic scales. Every orbital calculation adds to our understanding of the gravitational dynamics that shape object trajectories during million-year journeys between stellar systems. The multiplication we're witnessing transforms this archaeological expedition into something even more extraordinary. Instead of studying a single sample from interstellar space, we now have access to an entire museum collection, each specimen revealing different aspects of the complex processes that created their parent body and guided its evolution during its cosmic wanderings. As the fragments continue their divergent paths through our solar system, they're creating new chapters in humanity's ongoing exploration of cosmic mysteries. Some pieces will escape back to interstellar space within years, carrying with them gravitational signatures of their encounter with our planetary system. Others might become temporarily captured in orbital resonances with Jupiter or Saturn, remaining accessible for potential future study by advanced space missions. The possibility of sample return missions to 3i Atlas fragments represents one of the most tantalizing prospects in planetary science. Unlike meteorites, which have been altered by their passage through Earth's atmosphere and subsequent terrestrial weathering, pristine interstellar material could provide uncontaminated samples of alien stellar chemistry for detailed laboratory analysis. Such missions would face unprecedented technical challenges, requiring spacecraft capable of matching orbits, with objects following complex, evolving trajectories while operating at distances where communication delays make real-time control impossible. But the scientific rewards would justify the extraordinary difficulties potentially answering fundamental questions about stellar and planetary formation processes throughout the galaxy. European and American space agencies have begun preliminary feasibility studies for interstellar object intercept missions, recognizing that opportunities to study such material up close are incredibly rare and scientifically invaluable. The technologies developed for reaching 3i Atlas fragments could serve as stepping stones toward more ambitious missions to future interstellar visitors. As we stand on the threshold of the Mars encounter, the 3i Atlas story continues evolving in directions that challenge our most fundamental assumptions about interstellar objects and the processes that govern their behavior. What began as routine detection of another cosmic visitor has transformed into a complex narrative involving fragmentation physics, exotic chemistry, potential evolutionary optimization, and profound questions about the nature of materials that populate the spaces between stars. The upcoming weeks will bring observational opportunities unprecedented in the history of interstellar object research. But regardless of what specific discoveries emerge from the Mars flyby and subsequent observations, 3i Atlas has already revolutionized our understanding of what becomes possible when ancient materials from alien stellar environments visit our cosmic neighborhood. We inhabit a galaxy filled with wonders that exceed our most ambitious theoretical predictions. The multiplication of 3i Atlas demonstrates that the universe continues revealing new forms of complexity and beauty that reward our curiosity with insights into cosmic evolution operating across scales of space and time that humble human imagination. The fragments will continue their ancient dance long after they fade from our telescopes. Their chemical signatures preserved in scientific databases, their unexpected behaviors encoded in theoretical models, their multiplication patterns inspiring new questions about the diversity and sophistication of objects that call interstellar space their home. 3i Atlas represents far more than an astronomical curiosity or observational challenge. It embodies our species' ongoing dialogue with the cosmos, our persistent effort to understand our position in a universe that reveals new mysteries, with each advancing generation of instruments and theoretical frameworks. Through studying these ancient visitors, we glimpse the incredible diversity of worlds and processes existing beyond our familiar solar system, expanding our perspective on what remains possible in the vast, mysterious, and endlessly surprising galaxy we inhabit. The multiplication continues, the mysteries deepen, and our cosmic awareness expands with each new fragment detected and characterized. The universe has gifted us with 3i Atlas and its growing family of interstellar travelers, offering unprecedented opportunities to study cosmic processes that operate far beyond the boundaries of our local planetary system. In accepting this gift and investigating it with every tool at our disposal, we take another crucial step forward in humanity's greatest intellectual adventure, the quest to comprehend our place in the infinite cosmos that surrounds and connects us all. As these ancient fragments continue their patient journey through our solar system, multiplying and evolving in ways that surprise us daily, they remind us that we live in an era of unprecedented cosmic discovery. The secrets of interstellar space are revealing themselves through visitors like 3i Atlas, opening new windows into the processes that shape matter across galactic distances and deep time. The story is far from over. Each new observation adds another page to this unfolding cosmic narrative. Each fragment tracked contributes to our growing understanding of how the universe organizes matter across scales that span from individual atoms to entire stellar systems. 3i Atlas and its multiplying companions represent messengers from distant worlds, carrying within their ancient structures the chemical memories of alien stellar environments and the gravitational signatures of cosmic processes we're only beginning to comprehend. In the end, perhaps that's the most profound gift these interstellar visitors bring us. Not just scientific data or theoretical challenges, but a reminder of how much wonder still awaits discovery in the cosmos around us. The multiplication of 3i Atlas teaches us that the universe remains full of surprises, ready to challenge our assumptions and expand our understanding in ways we never anticipated. As long as we keep watching the skies and questioning what we observe, the cosmos will continue revealing new chapters in the greatest story ever told. The ongoing saga of how matter, energy, space, and time conspire to create the magnificent, mysterious, and endlessly creative universe we call home. The implications of what we're witnessing extend far beyond the immediate spectacle of cosmic fragmentation. As these pieces continue their ancient choreography through our planetary neighborhood, each fragment is essentially becoming an independent laboratory for studying the fundamental processes that govern matter when it ventures far from its stellar birthplace. Consider what this means for our understanding of interstellar chemistry. Every piece of 3i Atlas carries within its molecular structure a record of conditions that existed around alien stars billions of years ago. The organic compounds being released as these fragments warm in our sun's embrace represent chemical pathways that evolved under radiation fields, temperature gradients, and pressure environments completely unlike anything in our solar system's history. Dr. Amanda Torres from the Arecibo Observatory has been tracking the radio emissions from several of the larger fragments, searching for patterns that might reveal how these ancient materials interact with our local space environment. What we're detecting suggests chemical processes that don't match any terrestrial analogues, she explains, her voice carrying the excitement of someone witnessing something genuinely unprecedented. These fragments are teaching us about chemistry that operates under conditions we can barely simulate in our most advanced laboratories. The radio signatures she's detecting paint a picture of materials that have been fundamentally altered by their billion-year journey through the cosmos. Cosmic rays, stellar winds from distant suns, and the intense cold of deep space have created molecular structures that wouldn't naturally occur in any planetary environment. Now, as solar heating awakens these dormant chemicals, they're displaying behaviors that challenge our most sophisticated models of how matter should respond to thermal energy. But perhaps the most unsettling aspect of the 3i Atlas story lies in what it suggests about our cosmic neighborhood's hidden population of wandering objects. Statistical analysis of interstellar visitor detection rates indicates that objects like 3i Atlas should be relatively common, with several passing through our solar system every year. Yet we've only confirmed 3 such visitors in the past decade. This detection gap suggests either that our observational capabilities are far more limited than we realized, or that interstellar objects display such diverse characteristics that most pass through our system completely unnoticed. The dramatic differences between Oumuamua, Borisov, and now 3i Atlas certainly support the latter interpretation. Each visitor has challenged our expectations in fundamentally different ways. Oumuamua's cigar-shaped profile and mysterious acceleration remained enigmatic throughout its brief transit. Borisov appeared more familiar initially, behaving like a conventional comet until it began breaking apart in ways that revealed unexpected internal complexity. Now 3i Atlas is demonstrating multiplication behaviors that create entirely new categories of observational and theoretical challenges. This diversity suggests that the spaces between stars harbor populations of objects far more varied and sophisticated than our models predicted. Debris from disrupted planetary systems, fragments of stellar collisions, materials processed by supernova explosions, and perhaps even remnants of technological artifacts from civilizations that vanished eons ago. Each category would produce visitors with distinctly different observable characteristics. The multiplication we're witnessing in 3i Atlas forces us to confront possibilities that venture into territory traditionally reserved for speculation. While natural fragmentation remains the most probable explanation, the systematic nature of the breaking process has caught the attention of researchers who study the boundary between natural phenomena and potential technological signatures. Dr. Michael Richardson from the International Academy of Astronautics has been analysing the geometric patterns in the debris field for signs of organisation that might indicate artificial origin. We're looking for mathematical relationships in fragment spacing, synchronized behaviors across multiple pieces, and evidence of information encoding in the overall system architecture, he explains. While we must emphasize that natural explanations remain most likely, the systematic characteristics we're observing warrant investigation using the same rigorous methods we apply to any anomalous astronomical phenomenon. The possibility that some interstellar objects might represent technological artifacts isn't as far-fetched as it might initially seem. Any civilization contemplating exploration beyond their home star system would face the same fundamental challenges that constrain our own interstellar mission concepts. The distances between stars are so vast that any probe would need to operate autonomously for millions or billions of years. Such extreme longevity requirements might necessitate designs that could repair themselves, adapt to changing conditions, and perhaps even reproduce or fragment into smaller units when encountering target star systems. The multiplication we're observing in 3i Atlas could theoretically represent the activation of dormant subsystems designed to deploy only when environmental conditions indicate successful arrival at a stellar destination. But there's another interpretation that's gaining attention among researchers studying long-term cosmic evolution. What if the apparent sophistication we're observing results not from intentional engineering, but from natural selection processes operating over cosmic timescales? Objects that survive interstellar journeys lasting billions of years must possess structural characteristics that enable them to endure conditions that would destroy less robust materials. The harsh environment of deep space serves as an evolutionary filter, eliminating objects with unstable configurations while allowing only the most durable architectures to complete their journeys between stellar systems. Over cosmic time, this selection pressure might favor objects that develop internal organizations optimized for surviving both interstellar travel and the thermal stresses encountered during stellar system encounters. The systematic fragmentation patterns we're observing could represent the result of billions of years of cosmic evolution, producing structures that respond to solar heating in ways that maximize survival probability. Dr. Elizabeth Kumar from the Max Planck Institute has been developing theoretical frameworks for understanding how cosmic evolution might shape interstellar object characteristics. Natural selection operates wherever survival depends on specific traits, she notes. Objects that fragment optimally during stellar encounters would be more likely to produce debris capable of continuing to additional interstellar destinations. Over cosmic time, this could lead to populations with apparently sophisticated internal architectures. This cosmic evolution hypothesis offers a middle path between random fragmentation and intentional artificial design. It suggests that 3I Atlas might represent the product of natural optimization processes operating over timescales and under conditions that have no terrestrial analogues. Meanwhile, the practical challenges of tracking the expanding debris field continue to strain our global observational infrastructure. Each fragment requires individual monitoring to maintain accurate trajectory predictions, but the computational requirements are approaching the limits of our most powerful processing systems. The International Astronomical Union has established a special task force dedicated to coordinating global observations of the 3I-AT-LAS system. Telescopes across 6 continents now contribute data to a real-time tracking network that monitors fragment positions, brightnesses, and spectral characteristics around the clock. Dr. Jean-Luc Moreau from the Paris Observatory describes the unprecedented coordination effort. We're essentially operating a distributed telescope network spanning the entire planet, all focused on maintaining continuous surveillance of objects that are constantly changing their behavior and positions. It's the largest collaborative observation campaign in the history of astronomy. This global effort has revealed details about the fragmentation process that would have been impossible to capture with traditional single observatory studies. The continuous monitoring shows that new pieces continue to break away from larger fragments, creating what researchers describe as a cascade fragmentation process that shows no signs of slowing. Some fragments are developing their own miniature debris clouds, suggesting that the internal architecture of 3I Atlas contains multiple layers of structural organization. As outer layers peel away under solar heating, they expose interior materials with different mechanical properties, leading to secondary and tertiary fragmentation events. The spectroscopic signatures of these newly exposed materials are providing unprecedented insights into how interstellar objects assemble and evolve. Different layers display distinct chemical compositions, suggesting that 3I-ATLAS accreted materials from multiple sources during its formation or encountered different processing environments during its cosmic journey. Dr. Yuki Sato from the Japan Aerospace Exploration Agency has been studying these compositional variations for clues about the object's formation history. What we're seeing suggests that 3I Atlas isn't a simple agglomeration of materials from a single source, but rather a complex archaeological record of processes that operated across different stellar environments, she explains. The isotopic ratios measured in gas emissions from different fragments reveal formation around stars with dramatically different nuclear burning histories. Some pieces show signatures consistent with formation around metal-rich stars, while others display characteristics more typical of metal-poor stellar environments. This isotopic diversity within a single object raises profound questions about how such bodies assemble and what their presence tells us about material mixing processes operating on galactic scales. But perhaps the most concerning aspect of the 3I Atlas multiplication lies in its implications for planetary defense and space navigation safety. Each fragment now follows its own slightly different trajectory, and those differences will compound over time as gravitational interactions with planets perturb their orbits in complex ways. Computer simulations suggest that some fragments could become temporarily captured in resonant orbits with Jupiter or Saturn, creating semi-permanent populations of interstellar debris that might persist for millions of years before eventually escaping back to deep space. Other pieces might encounter planetary gravity fields that deflect them onto trajectories, bringing them closer to Earth during future orbital periods. Dr. Patricia Valdez, from the European Space Agency's Space Situational Awareness Program, has been modelling long-term orbital evolution scenarios for the fragment population. The chaotic nature of multibody gravitational interactions makes definitive predictions increasingly uncertain beyond a few years, she explains. What starts as minor trajectory differences today could evolve into major orbital variations that bring fragments into Earth's vicinity decades from now. And here we are, standing at the edge of one of the most extraordinary chapters in the story of cosmic exploration. 3I Atlas continues to defy our expectations, multiplying before our eyes as it races toward its encounter with Mars, each fragment carrying within its ancient structure the chemical memories of alien worlds we can barely imagine. Whether this multiplication represents the natural evolution of an exotic interstellar traveler, the product of billions of years of cosmic selection, or something that challenges our understanding of what's possible in this vast universe, one thing remains certain. We're witnessing something unprecedented in human history. Never before have we watched materials from another star system break apart in real time, revealing layer upon layer of complexity that speaks to processes operating across scales of space and time that humble our imagination. The fragments will continue their dance long after they fade from our telescopes, but the questions they've raised will echo through astronomy for generations. Each piece carries with it not just the chemistry of distant stars, but a reminder that the universe remains full of surprises, ready to challenge everything we thought we knew about the cosmic neighborhood we call home. Tonight, as you look up at the stars, remember that somewhere out there, in the darkness between Mars and the asteroid belt, these ancient travelers are writing new chapters in the greatest story ever told. The story of how the universe connects us all through the endless migration of matter across the galaxy. The story of 3I Atlas is far from over, and its greatest revelations may still lie ahead.